Wait, was it last
Yeah,
week?
you did it
Was that
last
the
minute
first one?
too.
Yeah, I
Yeah,
was
last
doing.
week was no, it was 2 weeks ago. We do it bi-weekly.
Oh, okay. Bi-weekly journal club.
Where's the share screen button?
Share screen is on the bottom. Record is right next to it.
Lego, stop. I don't actually see the shared screen button. Oh, there it is. I'm stupid.
Nice.
What?
Stop it, Lego.
You made a goal link.
Yeah, go links for everything, man. You can tell I'm a Googler because, or ex-Googler. I'm actually really, one of the things I regret is not taking my slide templates out from Google. Like, I really wish I had done that because I had some really good slide templates. Cool. Also, Jake, I actually think it'd be cool to upload some of these journal club things to YouTube. Depending on, I mean, I don't think there's anything too sensitive in any of these. So depending on the content, we can like review each one and then like decide whether or not we can upload them publicly.
This significantly increases the bar, the standard to which these presentations have to meet.
Hey, I've done a bunch of these actually, because when I was at Google, we did these like every 2 weeks, but nobody else ever wanted to do them, so I would just do them like over and over again. So like I've done like
coming to you for 30 minutes a week.
I've done like 40 of these at this point, so like, you get good at them after a while. Cool guys, thanks for coming to my TED Talk. Today we're going to talk about Clip, which comes from a paper out of OpenAI. It's a model that comes out of a paper from OpenAI. Actually, what is the name of this paper? I should actually know the name of the paper. It's I just closed that tab. The paper is Learning Transferable Visual Models from Natural Language Supervision. So this is a pretty cool paper. It came out when it came out. I think it's relatively new. Yeah, this was published in 2021, February 2021. So it's super new model. I think the code is actually online. I haven't had a chance to play with it yet, but the results are really cool, and it's definitely in line with like one of those like this is a really giant models type thing. So it can do a lot of cool stuff, which I think will be very relevant to us. So let's get started. Okay, so the 90-second view of this talk. So there's a lot of words in here that probably won't make sense, but unless you've read the paper already. But Clip uses a contrastive learning algorithm or contrastive learning loss to learn from this massive corpus of data that they scrape from the internet. I think it's like 400 million image text pairs, and it learns a joint embedding of images and text. So pairs of images and text should have high cosine similarities. Whereas non-pairs or things that are not actually related to each other should have low cosine similarities in the vector spaces. And Clip as a model generalizes really well to arbitrary data sets, and its feature space is really, really good, which means that it has actually successfully managed to learn the joint embedding of images and text pretty well, which is really cool. 90-second view, this is like kind of the key takeaways. So if you're like looking at the slide deck later on, this is kind of hopefully going to remind you, but I don't expect a ton of this to like make a ton of sense right now. Let's get into the background. So for people who've like read anything on my blog, they maybe have seen this picture before, but I think it's just worth covering again because I don't think we've ever explicitly talked about how I think about ML models in the past. So basically, ML models have three parts: features, embeddings, and losses. So the features are the baseline or the limit of what information a model can access. In the example on the right, we have a data set of shapes and colors. So the model is able to see some information about shapes and some information about colors, and it can use that to make some sort of a decision. The model is then composed of actual embeddings. So the model itself, you can think of it as just a stack of embeddings, and each embedding is a store of information. What do I mean by that? Well, when you have an embedding, you can think of it as a vector representation of some sort of data. The actual information is actually the same, like from an information theory perspective. It's just in a format that humans maybe can't necessarily understand. So humans are really good at understanding shapes and colors. We're not so good at necessarily intuitively understanding vector representations of floats, but the model can understand it, and that's what's important. And then finally, every model has a loss. So losses are these things at the end of the model, really throughout the model, but often canonically thought of at the end of the model that carve the embedding space. And the way I think about it is a loss is sort of a magnetic attractor for information. So you pump in a bunch of data that has a lot of noise in it. And the loss function is how the model determines which of this data is actually useful and which of this data it's going to throw away. And the corresponding linear transformations then transform that input over and over again through successive layers until the output is actually what we want. So it's one thing that's worth noting here, just thinking about like embeddings. You can see how these things all end up playing a role with each other on the right-hand side. We have two models with the exact same architecture, but the actual data that's being stored in the embeddings is different. So on the left-hand side, we have a model that's just trying to predict color information. And you can see that over time, the embeddings end up representing only color information or information that's relevant to color instead of the shape. Whereas on the right-hand side, you have a model that's just trying to predict the shape. It's not trying to predict the color at all. And so over time, and as you get deeper into the model, you end up losing a lot of the color information, and you only end up having information that's related to the shape. So this is what I mean when I say losses end up carving out the embedding space. So every single layer of the model, including the input features, represents its own unique embedding space. And a specific model activation represents a point in that embedding space, which in turn represents some more complex piece of data. What's neat about this is if you manipulate the features or you manipulate the loss, you end up changing how the information is stored in the embedding space. I tend to think of this as some sort of really high dimensional manifold. And what that essentially means is the shape of that manifold actually changes as you change the features in the loss function. And you can kind of see an example of this on the right. So the right-hand side is different layers of a convolutional network. And you can see, you can kind of figure out what the input was. The input was a picture of a dog and a cat. And in the bottom, on the top left, kind of going clockwise from the top left, no, actually, sorry, left to right, top to bottom, you have layers that are like higher up in the model. So the baseline layers of the model are all edge detectors. You can see that they basically are just trying to discover edges in the model, and you can see those activation functions light up. The next layer is trying to understand some sort of semantic understanding of like object detection. And as you get farther and farther up, you can see that the individual neurons in those activation layers end up becoming more and more high level. This is what I mean when I say that every single one of these layers represents a different activation space or a different embedding space. And you can kind of see from this at the convolutional level how each one of these layers can then build on top of each other or stack in order to create something that ends up being a high level object classifier. Also, by the way, feel free to stop me at any point if you guys have questions, just in case anything isn't super clear. Okay, so this kind of, let me actually fix this right now. This should be order sent back. Cool. So an embedding space is essentially a fancy way of saying like coordinate spaces, and 2D and 3D are also just essentially coordinate spaces. So operations that you can do in these spaces have high dimensional analogs. For example, if we have a 2D space, we can pretty easily conceptualize what distance between 2 points in a 2D space might be. There's a bunch of different ways you can do this, whether it be Euclidean or Manhattan or whatever. You can do the same thing in a higher dimensional space too, which allows you to calculate things like how far away two ideas are from each other, or how far away two different points in the embedding space are. This allows us to define relationships between different embedding spaces as well, because we can take these two concepts, as long as they have the same dimensionality, and compare them in order to see whether or not they have a certain relationship. All right, so that's all about like embeddings and stuff. I'm going to take a quick tangent to talk a little bit about different shot learnings. So traditionally, when we think of an ML model, we have this deep learning model that sees a whole bunch of data. And after it's seen a whole bunch of data during training, we then take that model and use it for some sort of inference related task. This is traditionally called end-shot learning. And it's kind of painful because for a given model, you have to train it over and over again every single time you have a brand new task. So if I want to take a binary classifier that can identify hot dogs, that's only useful to me in the hot dog, no hot dog case. If I want to take that same model and then try and identify stop signs, I would have to basically retrain it from scratch. Often we're interested in seeing how well a model generalizes to completely unrelated tasks. Like humans are really, really good at this, right? Humans are kind of traditionally seen as the canonical zero-shot learners. What that means is we can take things that we've like learned in school, for example, and apply that to the real world in situations that maybe we've never seen before. We want our deep learning models to be able to do this with as few additional data points as possible, ideally 0. So if you've ever played with like GPT-2, that is a canonical few shot example. You have a model that's been trained once really, really extensively, and then you can fine tune it on additional data by giving it more like, few shot examples. But 0 shot is like GPT-3, where you train it once and then you never have to train it again because it's just able to kind of do whatever you want it to do from that point on. I bring this up because in this paper, Clip cares a lot about 0 shot learning, and that's actually the entire goal of this paper. Okay, before diving into the paper properly, I do want to introduce 2 architectures really quickly that are going to be relevant. The first one is a ResNet architecture. So I'm assuming you guys have some background with like convolutional networks, or at least like broadly can visualize what they look like and how they work. On the left-hand side, we have an animation of a convolutional network. Basically, what it does is it takes these sliding filters over these matrices and then learns how to combine them in order to create the next level up. So when you have a stack of convolutional layers, you can basically combine these increasingly higher dimensional representations, which is similar to what we saw here. A ResNet is special in that it has residual connections between these layers. So some of the information that exists at the lower level ends up being propagated to higher levels as well. This is actually meant to solve a common problem that you see in convolutional networks, which is as you go up the chain and you kind of get more and more high level, you end up throwing away a lot of information from the initial model or from the initial input. And in some ways, this is actually the model working as intended, because remember what I said at the beginning, loss functions are kind of magnet attractors for information out of a sea of garbage. But in practice, sometimes it's worth having some of that low-level information around because the model might actually do something different with it. So that's what a ResNet is. A transformer is another kind of model that's also relevant here. Transformers became really, really popular in the last couple of years because GPT-3 and GPT-2 are both entirely made of transformers. And the reason they're really, really cool is because they take this concept of attention, which I'll get to in a second. They take this concept of attention and basically create an entire model out of just attention layers, which is fascinating because it's basically the most hands-off way of training a model. Like traditionally, when you build a model architecture, you try and enforce some level of constraints. For example, a convolutional network is pretty good at dealing with image tasks because you're constraining it to slide over the images in a certain way in the 2D space. And that allows it to interpret certain amounts of geometric relationships much more intuitively than, say, a multi-layer perceptron. This is also the reason why people use LSTMs or recurrent neural networks, because they have these built-in assumptions about how the data is supposed to look. Transformers are unique because they don't have these assumptions. They basically say, we'll let the model learn everything. And for a while, that was kind of like the holy grail, I think, of training models, is trying to remove more and more human biases. So I think transformers are really cool for that reason. Attention is kind of a weird concept, and I'm going to try and explain it as best I can, but it's totally okay if it doesn't really make a ton of sense. So the core idea behind attention is we want the model to apply some sort of probability weights to some sort of input in order to understand which of those inputs, which parts of the input are actually important. We call this attention because humans kind of do something similar. Whenever you're looking at something, say with your eyes or listening to something with your ears, your brain is actually taking a lot of input all at once, but it's manually filtering out stuff that's important. So when you're looking at something, you only really see the things that are directly you're looking at, maybe some stuff in your periphery, and you're not really paying attention to the stuff that's in your periphery. Similarly, when you're listening to somebody in a conversation and there might be cars going on outside, or driving outside, you aren't listening to the sounds of the car. You're able to focus on the person in front of you. Transformers try and get at the same idea by basically giving the underlying model at every single layer the ability to prioritize information. And the way it does this is through essentially a dot product and a softmax. So what I mean by this is basically imagine you have 2 vector representations of data. One is a vector and one is a matrix. If you multiply these 2 things together, you get some additional vector representation that somehow corresponds to how similar each element in the vector is to each vector in the matrix. If you then apply a softmax over this, the softmax basically takes this output vector, which is some scale of values, and converts that into a probability distribution. It basically squashes the vector so that all of the values sum up to 1. If you then, so this you can kind of think of as an attention vector. So Q and K in this image here, Q and K are a vector and a matrix respectively. And when you multiply them together and then apply a softmax on top of that, you are basically getting a probability distribution for how similar the vector Q is to each element in K, or each vector in the matrix K. That probability distribution you can then apply to other things, like for example, V, where V is some other matrix that you can then apply attention to. This is all kind of fuzzy, and the reason it's all kind of fuzzy is because the way backpropagation works, Q, K, V, and all of these weights in between will just sort of magically do the right thing. We don't have to think about how to constrain the model, because the model itself, through the process of training, will automatically assign these vectors and these matrices values that make sense for its purpose. So if it sounds a little bit fuzzy, that's because it is a little bit fuzzy. But what's neat is you can take this concept of attention and stack it over and over and over again until you get something that actually is really, really powerful, like GPT-3. Okay, so that's all background stuff, which I know I threw a lot at you in like 20 minutes, and I apologize for that, but it's totally okay if some of that stuff didn't make sense, because I think in future Journal Club presentations we'll be like kind of getting back at the same idea. Like deep learning only has like 3 concepts that are actually relevant. So, okay. So what is the problem that CLIP is trying to solve? The problem that CLIP is trying to solve is image classification, but it's not trying to solve just like a single image classification task. It's trying to solve all image classification tasks. Traditionally, when you solve an image classification problem, you have some sort of model and you have some fixed set of labels. And you can have a lot of labels. You can have hundreds of millions of labels, but the point is it's still fixed. And that's really frustrating because the space of images is massive. And the way you describe different images can vary immensely. What I mean by this is, let's say you're taking a very traditional model and you're trying to train it on MNIST. So your model is able to successfully predict whether or not a given image is a handwritten number from 0 to 9. Great, cool, we've solved that task. If I want to take that same model and then predict dogs and cats, it's just not going to work because the model has no concept of dogs or cats. It's only been trained on this set of 9, 10 labels. So as a result, we constantly have to train new classifiers for small task changes. And even if I want to just add a new label, like let's say I wanted to add 0, I have 0 through 9, and then I wanted to add the letter A, I would still have to basically retrain that entire model from scratch. So there's no robustness in the model, which really, really sucks. And more broadly, there's no good way for many image models to actually transfer learned behaviors to other problems. So the core intuition behind CLIP is, if we were able to co-train a joint embedding space where text and images are close to each other when they're related to each other, we could have arbitrary image classification, where for any set of classifiers, we just add new text to the underlying image space and then do a nearest neighbor search for images that are in the area, or vice versa. So how do you do this? Well, to start, you need the data set, which I think is like kind of the starting point for pretty much every ML problem. If you don't have a good data set, you're kind of screwed. To train a joint image text embedding space, you need image text pairs. And you can't just go with like a small number. You need a lot of them. So the OpenAI folks took a lesson from GPT-3 and they basically just scraped the internet. They looked for natural language descriptions of images where the text that was used to describe the image included one of a set of 500,000 queries. And they balanced this data to approximately 20,000 pairs per query, resulting in 400 million image text pairs, which is pretty cool. Like that's actually a lot of data. There's kind of a quote that some people in the ML world like to say, which is, a model is just a compressed data set. And so when you think of it from this perspective, if you have 400 million image text pairs, your model is actually representing a pretty large variety of data. And so it should be able to generalize pretty well to a lot of different tasks. Now, traditionally, we would use human labeling for this task. And actually at Google, they have this massive arm called human computation, which is basically just doing labeling. And it is incredibly expensive. A Mechanical Turk does the same thing. It's incredibly expensive, incredibly slow. But the benefit is those labels are really good because you can ask the humans to do exactly what task you're trying to solve. By comparison, OpenAI says, we're not going to do that because we need to generate 400 million image text pairs and we're not Google and we don't have free ad money. We're instead going to scrape the web. And web scraping is really powerful because it allows you to generate a lot of data from stuff that already exists out there. But the downside is that data is probably going to be biased in all sorts of weird ways because humans are biased naturally. And the data itself is not going to be very clean because when you're scraping images or text or whatever, you're always going to have these really weird outliers that are going to throw off your model. So you have this trade-off. Ideally, you could get a lot of data that's really high quality, but that's expensive. So in practice, you're either going to get a lot of data that's really shit quality and you just have to work with that, or you're going to get a kind of not that much data with really, really high quality. And then you can like train smaller models that maybe don't generalize that well. So OpenAI then looks at this and says, okay, we have 400 million image text pairs. We can't possibly have each one of these text things be its own label because 400 million labels would be just impossible to calculate in the traditional understanding of how classification models work. So instead, they use this technique called contrastive learning. Contrastive learning is different from traditional learning in that instead of outputting data, contrastive learning outputs a similarity score, namely a single float value. And basically, you can kind of think of this as like a binary task where you put in data from X and you put in data from Y from these two different distributions, and the model just outputs whether or not these things are similar. The reason this is really powerful is because it allows you to use relatively noisy data at scale. Because if you can generate 400 million image text pairs, for example, you don't have to worry about the computational cost of loading all of that data into the model at one time, like you would have to do if you were doing like a traditional MNIST classifier. Again, think about MNIST, right? Like the way that works is you put in an image and it outputs a value from, a vector that has a one-hot value from 0 to 9, basically. If you had 400 million different text labels, that vector would be size 400 million dimensions, which in turn means every single embedding underneath the model would have to accommodate that somehow, which would just be way too large. So contrastive learning setups are really, really ideal for large scrape data sets with no human labeling. The trade-off, of course, is that your model is probably, like your underlying embedding space is probably not going to be as good, but if you have enough data, maybe this will still work. So this allows us to kind of dive into the CLIP model in earnest. The CLIP model has two encoders. The first one is a text encoder, and the second one is an image encoder. The image encoder is a ResNet model. They actually tried a couple of different models, but for our purposes, we can just think of it as a ResNet model. And the text encoder is a transformer. So they basically take this input text and they convert it into a vector. And they take this input image and they convert that into a vector, and then they compare them. And what's neat about this is these vectors are the same dimensionality. So I think they're both, I don't know, like 64 dimensions or 128 dimensions, it doesn't really matter. But because they're the same dimensionality, that means they can be compared. And if you can compare them, because they live in the same embedding space, you can calculate a loss off of that comparison. And then from that loss, you can backpropagate down to the rest of the models in order to actually train your text encoder and your image encoder so that these two concepts live in the same embedding space. They're able to train a joint embedding similarity. So the way they actually construct this loss is, so let me take a step back. Once they've trained this model, they are then able to create a new classifier for any problem that they have by using the text encoder. They can basically put in arbitrary labels. The text encoder will then convert these into vectors. And then when you have a new image, you would again just do a nearest neighbor search on all of the nearby text images to rank how good they are in the underlying model's interpretation of the embedding space. So how do they actually train this model? Well, given a batch of n image text pairs, the CLIP model is trained to predict which of those n by n comparisons actually occurred. So if you have n images and n text, n sets of text, there is a n squared set of combinations where some of these actually existed in the data set and some of these did, and most of these did not. So the model was trained to maximize the cosine similarity of the image and text embeddings for the n actual pairs in the batch, while minimizing the cosine similarity of the embeddings for the incorrect pairings. And you can kind of see an example of this on the right. So if the image was of a dog and the corresponding label was dog, then the model is trying to maximize the cosine similarity of these two vectors. Basically move these two things closer together in the vector space. Whereas if the picture was of a dog and the label was of a pizza, or the corresponding text was of a pizza, the model is going to say, hey, this didn't actually exist anywhere in our data set, so we're going to try and make the cosine similarity of these two concepts lower, and so spread them farther away in the underlying embedding space. There are a few other details. They actually trained a bunch of ResNet and image transformer models for 32 epochs on the data set. So that means they saw, each one of these models saw the 400 million image text pairs 32 times. They used Atom, which is like the default optimizer. If you're using anything other than Atom to start with, you're probably doing something wrong. They had a batch size that I don't understand why. Like, is this a power of 2? I feel like this must be a power of 2. 32,768. I don't know. They used some weird number for their batch size for some reason. It's not a power of 2. Okay, I don't know. And their largest model took 18 days to train on 592 GPUs, which is a lot. How many is that? I don't know. How many GPU
Oh, wait,
years
32,768 is a power of 2.
Oh, it is a power of 2? Okay, so that's probably why they did that. Yeah, so 18
GPUs. That's like, because what, it's like $4 an hour for a GPU.
I'll take your word for it.
How much
yeah, this was expensive. This is an expensive model.
And this is just for the baseline, right?
Yeah, so they did this is just for the largest model. They did this for a bunch of different models. So like the overall training process for this paper was probably something on the order of like millions of dollars, right?
Yeah, it's just $1 million for that one line alone.
And that's assuming that they like got it right on the first shot, which like they probably did.
Right. This is just like the last stage.
I will say like this is like the craziest thing about Google is like, and like OpenAI and like these companies is like, this is just like peanuts to them, which is like crazy. It is crazy. Anyway, yeah, nothing feels quite as powerful as spinning up a model that has like, that costs as much as like a small country. Okay, so let's talk about some of the experiments and the results that they had. So the main thing that they cared about was zero-shot transfer, which was basically, can we load other data sets labels into CLIP and see how well it performs? And so you can see the examples on the right. They basically ran this on, I think, 27 different data sets. Some of these are like very specific, like Stanford cars is like, here's just a bunch of pictures of cars, can you rate them? Oxford pets is like, here's a bunch of pictures of pets, can you get the right labels? And then Eurosat, I think, is like really cool. That's actually like a satellite data set. So that was like super different from like a lot of the other stuff that they've seen in the underlying like model. But you can see actually like CLIP does reasonably well. So they compare this against a linear probe. A linear probe is basically you take a ResNet feature, or you take a ResNet model that already has been pre-trained. ResNet is like, like a pretty popular image classification model. So like it's already been pre-trained, I think, on ImageNet. They take those features and they train a linear classifier on top of that for each of these data sets. And CLIP outperformed that model on 16 out of 27 data sets, which means its feature space was better than ResNet 16 out of 27 times without any additional training, which is really cool. Whereas the ResNet model did have additional training, the linear classifier saw all of the examples of the data set until it reached a convergence. What was kind of interesting about this, I thought this was interesting, was they actually had to do some prompt engineering. So it wasn't enough for the model to just be like cat, dog, pizza, because in their underlying data set, it was very rare that an image was described as a single word. In practice, because they were scraping from the internet, the image was often described as a photo of a dog or a photo of a pizza instead of just dog or pizza, which is really weird and actually kind of cool. It's kind of like, again, getting at this idea of like how you query the embedding space actually matters a lot based on like how the model is trained. Similarly, for Oxford pets, for example, they observed like, I think like a 5% improvement if they said like a photo of label a type of pet. Like adding that additional context helped the model pinpoint exactly where in the embedding space it was supposed to be, which in turn resulted in a significant improvement in its performance. So that's pretty cool. They also compare, so this is zero-shot transfer, which is like, if you're not learning anything at all, and you're just using CLIP, how well can it do on like a bunch of different data sets? They also cared a lot though about the underlying representation. So one thing that they wanted to check was like, what happens if you actually then if you actually do supervision on top of CLIP, you take those features and then you learn something on top of it with the basic linear classifier. And here you can see that actually the model performs really, really well across pretty much all data sets. except for the ones that are like really, really, really highly optimized. So like ImageNet, CFAR 100, CFAR 10, like these are like really, really popular data sets. And so the models there are often like very highly optimized for that. Whereas Clip was not optimized for that and is still able to outperform and like perform reasonably well to ImageNet, for example, on like pretty much everything. What is the hateful memes data set? Whoa, that is interesting. What is that data set? Wait, I'm very curious. Hateful memes. Is that like a Facebook AI?
Yeah.
That is so fascinating. Okay, I need to look at that like in the future. Okay, so this is another experiment that they did. They were actually really interested to see how well Clip could handle distributional shifts. So one thing that I kind of mentioned is like, models are not super robust because they represent the data that they are trained on. And so if you train a model that's like on ImageNet, it will learn to predict pretty well on other images that look like images that are in ImageNet. But if you were to give it something that looks completely different, it'll actually perform really poorly. A good example of this is like if you have a model that's trained on ImageNet, a ResNet model that's trained on ImageNet, it's able to get like 76% accuracy on the raw ImageNet data. But if you try and use a different data set like ImageNet Sketch, where it's using sketches instead of like actual pictures, the accuracy drops to 25%, which is really, really low. Clip does not have this problem. And again, Clip here is doing zero shot, so it's not even like looking at any of the data at all. This is just from the previously trained data set that it had. And I like this one. I thought this was just really funny. So they also compared against like humans. They were like, hey, how good are humans at like predicting whether or not pets are of a certain species, like certain breeds of dogs or something like that? And they compared against like one-shot humans, zero-shot humans, which is like they've never seen a picture of that that thing before. So like if the human knows the breed or whatever, then they know. If they don't, then they don't. Then like one-shot humans, where it's like, okay, this is an example of this breed, now go. And two-shot humans, which is like, here are two examples of this breed, now go. And like humans apparently suck at this, but zero-shot Clip is like really good. So zero-shot Clip is able to outperform on like predicting different dog breeds, having never seen any of those dog breeds before, with like 93% accuracy, which is like 20% better than humans. So I don't know. I just think that's like really, really funny that they tried that. Also really funny too that like they called it two-shot human. Like I don't know. Anyway, whatever. There was supposed to be a picture
really,
here.
Terrifying in like the confidence that comes from seeing that 93, but then the like crazy historical level aberrations that will come from like then making mistakes on the like last 6.5%. Like for example, like, oh, Clip said that this was a Pomeranian, and like as human beings, like as a civilization, we've totally forgot what Pomeranians look like. So we'll just believe you. Okay, cool. It's a Pomeranian. Might not be.
I mean that's like a really like sort of benign example of this. Like there is definitely a risk to like over trusting these models, but I don't know. I mean, like, but on the one hand, like this is still like a zero shot thing, right? Like it's kind of like if you just asked a random person on the street of New York, like, hey, what kind of dog is this? First of all, they might be like, why are you? They probably wouldn't answer because it's New York. But second, like we wouldn't necessarily expect them to do that well. So it is interesting that like it's able to replace humans, but also it's like maybe if a human ingested 400 million image text pairs, it'd be able to do better. I don't know. It is very interesting though. I think like I have fuzzy thoughts on like the implications of this table, but none of them are like concrete. So I don't know. Anyway, very interesting stuff. Okay, so there's a few downsides. So I thought performance, they actually complained a little bit about Clip's performance, which I thought was interesting. So they basically said that like, hey, Clip does really, really well against this like linear probe, but in general, it's actually not doing state of the art, which makes sense that it's not doing state of the art because again, like you're competing against models that have basically been fine-tuned on a specific data set. But ideally, Clip would be able to get state of the art just from being able to learn some sort of generalized thing. So when it's comparing against models that are like really specially tuned for a specific data set, Clip still does not do that well. I think Clip's real value is the fact that it's generalizable. It's interesting too that they like look deeper into the sorts of image data sets that like Clip kind of performs poorly on, and it's those that involve really fine-grained classification. So what I mean by that is, traditionally in the image classification space, you can have like rough or very coarse classification, which is like, this is a dog, this is a cat. And you can have fine-grained classification, which is like, this is a Pomeranian, this is like a West Highland Terrier. And obviously the fine-grained classification is harder because not only do you have more labels, which involves more possibility for mistakes, but you also have a larger amount of like calculations that you have to do, and you have fewer examples per each individual label. So you might have like 1 million examples of dogs, but you might only have 10 examples of a West Highland Terrier. So Clip does really, really poorly actually on fine-grained classification, which is not surprising. Like the Eurostat thing is like a fine-grained classification task, but they obviously want Clip to do really, really well on like natural language in general, which is actually quite admirable. So I'm very curious to see how they like kind of improve on that. Another interesting performance problem is that Clip actually does really poorly on out of distribution stuff. So what I mean by that is, in distribution is like the sorts of things that the model has seen during training time. Out of distribution is the stuff that it wouldn't have necessarily seen during training time. And this is again a great example of like why it does poorly on Eurostat. It probably does not see a ton of satellite images in its underlying training data, so it's going to perform poorly when it sees a bunch of satellite images and is trying to classify them. A really good example of this is the MNIST data set. It didn't see a lot of handwritten images on, when it was doing its training, so it only got 88% on MNIST, which is frankly abysmally low when you think about like the state of modern machine learning. Okay, so that's like performance problems. Clip actually also has an interesting problem on the concept side. So the dream of Clip is actually natural language generation, which is given an image, it's able to generate a novel caption for this image just based on the embedding space. So it's able to basically query the embedding space for a generative model instead of just having a embedding model. And unfortunately, it can't do that right now. You have to prime Clip with a set of labels in order for it to then do a nearest neighbor search on top of that set of labels in order to actually calculate which images, which text labels are, closest to which images. So the long-term vision of Clip is to eventually be this thing that you can just like throw in any image and it'll like able to query the corresponding text and generate the text that would like make sense for that image, and vice versa. So you describe some text that is able to generate the image that like would live in that part of the embedding space. Right now, it's just purely classificational. So you have to give it the data points in those embedding spaces for the model to actually understand. And then finally, like, this thing is super expensive. Like, what do we say? Like $1 million for like one version of this model? Like, yeah, that's a lot. Okay. So how is this relevant to what we're doing? Well, I think it's kind of obvious. Hopefully it's kind of obvious. So much of what we're doing is related to search, right? Like we're like basically trying to work on searching for data. And Clip is a very natural way to enable text search. Frankly, like, or I should say like text image search. So frankly, like this is actually very, very similar to like what Google's doing under the hood too. Like this is the sort of technology that does power like Google image search. And having the ability to like jointly embed text and images in general is very, very powerful because it allows you to kind of like humans think of these things in terms of ideas. In our brains, we've already done this process of like having this joint embedding space. Allowing a model to do this brings us one step closer to kind of just communicating naturally the way we think to the model directly, which in turn enables a whole bunch of really nice HCI, UI, UX experiences that are much more natural to an end user. But more specifically, I think the joint embedding itself is really nice. So the long-term vision for us is to visualize different types of data in the same space, whether it be images or documents or whatever else. Clip kind of lets us do that with text to images and provides a framework for doing this for other types of data. So we might not necessarily rely on the Clip model for images and video, but you can imagine that same contrastive learning, embedding type understanding of how to actually construct a loss and then train a model could be useful for arbitrary types of embeddings. And frankly, you could even imagine a data set that is like, combinations of pairs of images and text and images and video and text and so on and so forth. And as long as you have the right embedding models, you could use this kind of a loss function in order to actually train a joint embedding space across all of these concepts. Ridiculously expensive. It would be incredibly expensive, both to generate that data set and to train that model, but it would be really, really powerful. And again, I think Google is actually trying to do something like this under the hood, which is pretty cool. So this might be one of those things where, like, if we wait a year, the technology is just going to appear on its own, and we won't have to spend any of that money or time doing it. We can just take like whatever fancy model is like, available online. We can just take the models and model weights. So yeah, so that's it. Hopefully this was informative and interesting, and not too confusing or like technically jargony or anything like that. So just as a quick recap, CLIP is this model that is basically using this contrastive loss and this massive data set, 400 million image text pairs, to learn a joint embedding space. And then from that embedding space, it's able to generalize really, really well to brand new tasks and data sets and images and text labels that it's never seen before. And this is really powerful for us because we are actually very much in the business of thinking about how to query embedding spaces and how to generate them for semantically meaningful and useful tasks. Yeah.
You're thinking like in a year, we'll be able to just like hit an API that OpenAI has or something, or like Google has, that'll let us like do this?
I don't know. I mean, some of these models are really big, but like I think the CLIP model is actually publicly available.
It's already public.
So GPT-3 is something that like, okay, like they've closed down and like we have to like have an hit an API, but there are like open source versions of this that people are trying to generate and stuff. So I guess to answer, maybe I'm like missing the forest for the trees in your question. I think that this technology will probably be available in a year. Whether it's in API form or a model that we have to run our own is kind of irrelevant.
Cool.
I think, in some ways it poses a really kind of challenging conundrum, which is that if we build something like CLIP into the like core fabric of our product offering, and we rely on an external company whose motives are slightly unclear and who like might change their mind, like, do we introduce the possibility of like basically existential risk down the road by not having these models built in-house?
So, I mean, in some ways, I'm kind of like less concerned about that. Like, I think if like somebody eventually, this is just like the nature of computer science, things will eventually be open, right? And so like eventually somebody will release a version of the CLIP model online, and maybe it's not perfect. Like maybe it's not as good of an embedding space as like the latest and greatest, but this is like, I almost don't think it matters. Like the incremental improvements on embedding spaces in that like somebody like Google will have compared to like what the default is frankly not enough to be even like noticeable to the user. Like it will definitely improve some metric at scale when you have like millions and millions and millions of like users or something. But like when you have like for the individual user, it's much more important to nail the HCI and the UI UX and the tooling around that makes it more important. So I actually think that like where we would have a competitive advantage potentially is in the tooling that we build to query the embedding spaces instead of improving the embedding spaces themselves. Does that make sense?
Yeah, totally. Which leads to another thought and question around like one of the opportunities I think that we'll have is like a very specific data set.
Yeah.
Very specific interactions. And
yeah.
Do you see that as being an opportunity for providing, like a really valuable set of refinements on top of CLIP, for example, or, some other model where we're, able to extract that extra, like X% performance for our particular use case because we have such a unique data set and these other interactions that we can use to like inform.
Yeah. So fine tuning is something that's like, so actually I do want to, this is sort of interesting. Fine tuning is almost always like conceptually better because you're training your model to like more easily represent or like better represent the actual task that you're trying to solve. In the paper, they actually discovered that like few shot learning where N was less than 4 was actually worse than zero shot learning, which is fascinating and totally unexpected. So I know that this doesn't like directly answer your question, but like to more directly answer your question, I think that like our unique data set will definitely be helpful and we should totally like fine tune our models, whatever it be. eventually we should fine tune these models on the unique data that we have. In practice right now, meh, like that fine tuning is probably not worth the amount of cost it takes. I think my experience with ML models, especially for like actual infrastructure use cases, is like you can't rely on the ML model to be perfect. ML models are so fuzzy. They don't like hard boundaries. They don't like discrete things. They think of everything in terms of continuous metric spaces, and they're very, very fuzzy. And so as a result, you can try and perfect the model as much as you want, but it'll never quite be perfect. And at some point, you are better off building in the assumption of failure and building infrastructure that accounts for that failure and works around it or allows the user to work around it. This is like, in my mind, this is not so dissimilar from like, Google's, approach to dealing with like hardware at massive scale. At some point, they were like, okay, we're dealing with so many hard drives and so many CPUs and so many, different pieces of hardware that eventually something will fail. So instead of trying to assume that everything will be perfect all the time, we're just going to build something that is like more resilient to those failures. I think the same thing applies to ML. You can't assume that the model will always be correct, and trying to eke out 1 or 2% improvement, in my mind, really belongs to the domain of academia. Like, it's just not relevant for infrastructure. For the most part, infrastructure folks should be working on building fault tolerance and making your models more robust so that the user doesn't actually notice those mistakes and can work around them when they exist, instead of like, automating everything and like assuming the ML model will like be perfect every time.
Okay.
Yeah, I agree with that take a lot. And like the interface design is like, yeah, how do you give context to the limitations of the model or design around them?
Right. I think also in some ways, like, well, so two things. One is like the user is often very willing. I mean, we've observed this in the past. The user is very willing to construct narratives.
Yes.
So regardless of like the model's like mistakes, like the user is willing to construct narratives and like observe like why the model did what it did. And I've kind of joked about this in the past, but I kind of think that like if you gave a totally random set of images and we're like, this has structure, people will be like, oh yeah, I see it. Like, I mean, obviously we shouldn't do that, but like kind of an amusing like thought process. And like maybe at some point we want to actually A/B test that. But yeah, so I think the main UI challenges are about like kind of working around the limitations, but also, like I said, there is a certain magic in thinking about an embedding space like an oracle. So the way I kind of think about these models is like, you have this all-seeing, all-powerful thing that has a representation for all of the data that could possibly exist. I mean, obviously this is like a little bit of an exaggeration, but when you're training on like 400 million image text pairs, functionally that's the case. Like, it has somewhere in its weights the ability to understand every possible like iteration or combination of data out there. And the more data you train on, the larger your model is, the more true that becomes. So it becomes less about, in some ways it becomes less about how do you construct a better model and more about how do you give the user the right tools to query the model that already exists. Not to talk too much about Google, but like again, like Google had this problem too, where they were like, hey, we have this massive corpus of data that functionally consists of all of the information in the world. How do we properly query this? Like, what is the best way to allow a user to query this information? And the refinements that they made around like text search, including things like, did you mean, right? Like if I misspell something and then it tells me like, did you mean X? Like, those are all parts of the sort of UI UX problem of how do you actually query an oracle that just has all of the information already existing.
Yeah, and this is also making me think, like, I think we have a good start because we're representing it as a space. Like a representation is a simplified embedding space, but it is that embedding space, which is in a lot of ways, I think, closer and easier than if we were trying to like just present a list view and be like, these are all dogs, and you see some non-dogs in there. Like, we're already giving more context of like how the similarity works. Just nice about this approach.
Cool. Okay, so if nobody else was...
Can we make these meetings an hour, like in the future?
Yeah, we can make these an hour. I also like nobody actually ate lunch during this meeting, so.
Yeah, I don't want to
I
interrupt.
did.
My lunch.
I did.
Oh, you did.
Oh.
When we have an actual office space, it'd be cool to like actually like bring lunch and sit.
This is great. Amol, were you guys storing this stuff?
The recordings?
Yeah.
Go/JC recordings.
Okay. If it's possible, I really like having in like meeting notes be this like central repository for any time we gather. So I might copy, like, could we copy your slide deck and like put it there?
Sure. You mean all the links and stuff?
Yeah.
Yeah, we have there's a go/JC schedule is like what we've been using for scheduling and stuff, and it has like all the relevant information, so we can copy that over.
Okay.
Cool, guys. I think that's it. If nobody else has any questions, we can call it.
Cool.
Yeah.
All right. Thanks,
Yeah,
folks.
Doing it.
Yeah,
That's good.